I'm back, and if you recall, in a previous lesson, we talked about the silicate minerals. And we started off with isolated silica tetrahedrons, and we said that they could be glued together, and then that made the mineral olivine. All right, so if you look at that picture there, you can see olivine is in the top left-hand portion of that picture. Okay, then the next thing that we said was you could take the silica tetrahedrons and you could put them together into a chain. Okay, that turns out to be pyroxene. And then we said that you could take two chains of silica tetrahedrons and glue them together, and then that turns out to be amphibole. And then we said that you could take multiple chains and put them side by side, and then you had a sheet. And then that was mica. And then finally, you could take the silica tetrahedrons and you could hook them together three-dimensionally so that you have this three-dimensional mineral, and then that's going to be the quartz and the feldspar. Okay, so those were all called the silica minerals, the silicate minerals. And like 90% of all rocks are composed of just those minerals. So there was a guy by the name of Bowen, and he was the one that came up with this Bowen reaction series. And so it shows that if you start with a magma at a very, very high temperature, so we start at a temperature of around 1200 degrees Celsius, and everything is a liquid. Okay, it's a liquid melt. All right, then what we're going to do is we're going to start to cool it off, and it turns out that the first mineral that is going to change from a liquid to a solid is going to be olivine. And so if you have a rock that, and we take that melt and we freeze it just like that, then we would end up with a rock that would be composed mostly of olivine. And then you also notice it's going to have a little bit of plagioclase feldspar. Now, the thing about plagioclase feldspar is that it has a range of different chemical compositions. So you can have plagioclase feldspar that has a lot of calcium in it, and then you can also have plagioclase feldspar that doesn't have calcium, but instead it has sodium in it. And so there's a range of different kinds of plagioclase feldspar. So at first, the first kind of plagioclase feldspar that's going to form is going to be the kind that has a lot of calcium in it. So it's calcium-rich plagioclase feldspar. And so if we were to freeze the melt when it's composed mainly of olivine and calcium-rich plagioclase feldspar, it would be an ultramafic rock. It's going to be extra dark. So do you look at those minerals? Do you see that olivine and pyroxene and amphibole, that they're dark minerals? And so therefore it's going to make a dark looking rock. So that's going to be an ultramafic rock. All right, but on the other hand, let's say that we, instead of letting this thing cool off very quickly, let's let it gradually cool off. Then what would happen is that the olivine is unstable at lower temperatures. It doesn't like the lower temperatures. So it will tend to fall apart and into those silica tetrahedrons, and then those silica tetrahedrons will then recombine to make pyroxene. Okay, meanwhile, with the plagioclase feldspar, some of those calciums are coming out of the feldspar and they're being replaced by sodiums. So now we've got if we were to freeze this melt, we would end up with something that is composed mainly of pyroxene with a little bit more sodium plagioclase feldspar. And that is going to turn out to be a mafic rock. It's going to be lighter in color than the ultra-mafic rocks. Okay, then the next thing that's going to happen is if you, again, we cool off this melt very slowly, then what would happen is the pyroxene would begin to dissolve and it would reform as amphibole. And then, again, some of the calciums would come out of the plagioclase feldspar and it would be replaced by more sodium. And then what you end up with is an intermediate kind of rock. Finally, and so then this is also where mica is coming from. So an example of a intermediate rock would be like andesite. So andesite is kind of, it's not really dark like an ultramafic, but yet again, it's not really light like a felsic rock, like granite. It's in between. So finally, we're going to allow this melt to finish crystallizing. And so the final minerals that you would end up with would be, this time, potassium feldspar, muscovite mica, and quartz. And then these combination of minerals tend to make the felsic rocks, felsic igneous rocks. So in our next segments, we're going to talk about these kinds of rocks individually and what they're composed of, and then what do they look like. Okay, so that was Bowens reaction series. So I will see you then in our next segment where we want to compare olivine and quartz.